So thank you for coming, dear students. Today we will have second lecture of the course of deep learning, where we will talk about the first architecture of neural networks, dense neural networks. First of all, motivation. Why do we need them? And major motivation is to separate classes with nonlinear class borders. As you see here, the red dots and green dots, they are very non-trivially distributed, and it will be very hard to separate them with any of the simple classifiers and decision borders, like linear one or a convex one or polynomial. You see there is no polynomial dependence, there is no linear dependence, etc., etc. So for these kind of tasks, where you have a very complex function that doesn't fall in any of the buckets of the known functions and typical ones, we need algorithm and architecture that is called neural network. Neural network is known as universal function approximator, namely the framework that fits almost any kind of function, well, almost because you need to know how to implement it and how to develop the network to fit the task. By the way, feel free to ask questions in the chat. You should see, so you can type it and I open the chat, I will try to answer. So the artificial neural network, I told you on the last lecture that it was inspired by biological neurons and how they connected in our neural system. And these mathematical models, they consist from several typical elements. In front of you, you can see the typical structure of a neural network with input layer in red, output layer in green, and hidden layer in blue. Input layer and output layer are mandatory elements of neural network, while the hidden one, it can vary in size. It can be thickness of one layer, like two and more. And also it can take a very complex forms. Yeah, so let's talk about each of the layers in more details. First, input layer. Input layer defines how many features the network uses. Pay attention that this number is static. Once we decided how many features the network uses, we cannot change it. In this case, the network uses 3 features. If we were to estimate a renting price of a flat, right? These features could be square, like area, how many windows, and proximity to the center of the city. 3 features, right? And we train network on these 3 features. If we want to have 5 features, we need another network. Okay, we cannot change this one because it works only with 3 features. Next, output. Let's take the same task. We are predicting price of renting a flat, and I told you that we are predicting price, right? Price is a continuous value, and we need 1 neuron for predicting continuous values because they will just predict the number. In this case, we see 2 neurons, right? Who can guess which task can resolve this network?
A classification.
Oh, yeah, it's written there. Thank you. Yeah, this network can do classification. In our case, it can say, is it expensive flat or is it cheap flat? Like 2 classes, right? Yeah, so when you have for each class, you need to have a separate neuron for this class. In case of dense neural networks, if you have 1 output neuron, you can have either binary classification if you put there a log loss, sigmoid, or you can have regression that predicts 1 number. Okay. Typical question here: how many hidden layers and neurons I have to pick? With inputs and outputs, it is more or less clear. Inputs, how many features do you have? Outputs, how many classes do you have? Or if you have two classes or a continuous value, then you have one neuron. Okay, that's clear. But what's with the middle layer? What was the hidden layer? Yes, please.
I'm sorry, I wanted to ask about previous one, output layers. If we have a classification and we have example of cheap and expensive flat, isn't it a binary classification?
Yes, it depends how you implement it. It's a binary classification with a sigmoid loss, or it's a cross-entropy loss on two neurons. You can do it in either way.
Okay, thank you.
But thank you for question. Yeah, good. Attention is good. So it depends, to summarize, on the type of a loss function that you, or activation function that you put on the last layer. In the case of last layer, it's called loss function because it will help you calculate how far you are from ground truths. Yeah, large value, you're very far from ground truth. You need to change your weights more. A smaller value, you're closer to the ground truth labels. Then your deltas for gradients will be smaller and smaller. This is core concept of mathematical optimization. Okay. Now, in regards of the hidden layers, choosing the structure, the size, and the number and activation function of hidden layer is science. Even not science, maybe it's art, because it's semi-scientific, to be honest. You can make it, there is no one theory behind how you build the structure of artificial neural network for some particular task. In every case, that's a different task. And if you resolve one classification task, it doesn't mean that you can take the same thing and resolve another classification task. In case of another classification task, it will be another structure, another parameters, and you have to do it from the very beginning every time. With some experience, you accumulate some intuition about how many layers and how many neurons in the layers you should have and what activation function, but not more. So I call this art. Right? Then, okay, is it that simple? Not exactly. There are one additional thing, that is like several actually. One is there are activation functions in each neuron. See, those annotations, I uppercase, IG lowercase, they stand inside each neuron to show that there is some function that works with activation, raw activation of a neuron. Remember previous lecture, I told you that the neurons, they simulate neuron cell bodies, which collects all the excitation from surrounding cells of previous layer, right? And then they make a decision, should they pass this excitation to the next neuron or not? So this process of collecting excitation from previous layer, you can see depicted in weights. See these connections, arrows. They are weights, right? The weights is something that you learn in this neural network. And the activation function is a hyperparameter. You pick activation function. The default one is ReLU, Rectified Linear Unit. The major task of activation function is to make the neural network nonlinear. If it's linear, then it degrades to a system of linear differential equations, right? You can solve them with a Cramer rule, Gauss rule, and or others, or matrix decomposition, right? That's not a smart system anymore, and now it cannot fit complex nonlinear dependencies anymore, right? So you need nonlinearity here, and then the linearity part is activation function, right? And the intelligence counterpart is a combination of this nonlinearity, many layers of neurons, and many connections between all the neurons in previous layer with all the neurons in the next layer. And this is where the names come from, because it is dense or fully connected neural network. Dense, see, it's dense. Everything is connected in the previous layer, connected with everything in the next layer. Signal goes from J to I. Signal and data propagates from input layer to hidden layer into output layer. It should remind you the synapses, see? Synapses is a connection of one neural cell to another neural cell. In this case, this is a simple. This is one neural cell, it connects with another neural cell, and this is a place of a connection, a synapse. Right? In math, it is brutal addition. So there is only addition. See? Now, how it is emulated. Let's look at one neuron. You can see it here. Inside, you have a cell body and activation function, this activation function in red. The activation function here depicted as f. As you see, this f takes as a parameter a sum of weights multiplied per corresponding parameters plus bias. Weights are weights of the connection between neurons. Parameters are x's that are incoming data. In our case, we selected area of the room or flat, number of windows, and proximity to the city center. So area, proximity to the center, and number of windows. See, all these parameters come inside the cell body, and they see, let's say, x-axis, the number of windows, and proximity, they are multiplied per parameters w. W, weights of connections. Then they are all summed up. As you see, no magic. You just multiply pairwise corresponding parameter to corresponding weight, plus another parameter to another weight, plus another parameter to another weight. You sum it up, and you add something that is called bias. Bias is a bit harder to understand because it should remind you the linear regression, multi-parameter linear regression function. The bias is to disassociate the line from the center of coordinates. So it can cross any of the axes like higher or lower than a zero. Then this distance will be biased. As you see, it's without axis. So there are no parameter that is multiplied per another parameter to make it biased. Same as linear function. You remember, y equal to kx plus b. Kx, well, k is a tangent of an angle, yeah, and plus b is where the line crosses the y-axis. Same here. So then you multiply, then add everything up, and then you pass to activation function. Activation function could be hypertangent, linear, rectified, linear, unit, step function, many other. Okay, is it clear? Any questions?
How do we set up weights for every neuron and every connection?
Good question. How do you set up weights for every connection? Not neuron. I assume that when we start training, and the answer is that we give them some numbers between 0 and 1, some very small random numbers. This is a default strategy. Then we say, hey, we don't know what are the weights. The weights will be the parameters of this very component nonlinear model that will describe this dependency. Yeah, I don't know the weights. I want the network learn it, right? So what I do, I put here some random numbers, and then I create another algorithm that upgrades, makes this number better until they do what I wanted to do with separation of this data, right? So this is one algorithm, and then I need another algorithm that will update the weights. Okay, that's a optimization task, like Adam. Remember, maybe somebody will play it already.
Sorry, and so what is going to happen if you just avoid bias?
All your parts will stick to the center of coordinate. They will cross y-axis in 0.
And why is this bad?
I think that it is bad because of the function will not have enough freedom parameters to feed the dependency that you want. Feel free to try it in experimental setting. In each layer, you can say add bias or not. You can avoid adding bias, and you will have them without B. But you will never see those numbers. This is theory that is behind. It is implemented by framework developers, but you will not see it in reality. You just need to understand, must understand what's behind to effectively use it, okay? And one more thing that is not straightforward is this X0, W0. This is a kind of fake neuron with W0 and multiplication per 1. X0 is not one of your features. X0 is just the 1. It's additional plus 1 feature just to multiply per bias. W0 is bias. See, W0, X0 is B. Actually, no. Actually, that's different. So each neuron has bias. It's in the form WX0, and then each layer has a bias. So there are two bias terms. Maybe not very clear. So each layer is a vector, right? And this vector is passed into activation function as a whole because all the functions are vectorized, right? But before all these values are combined into vector, they are summed up individually. And this is additional term to debias every neuron, and then you have B for a layer, for a whole layer. Okay. So what happens? You have features. Features are multiplied per weights. Everything is summed up, biases are added. Then this value, it will be a number. It will be 10, 50, 78, 99 per 75, whatever. It will be a number. This number will be passed to an activation function. Activation function, for example, ReLU. ReLU is very simple. If it's larger than 0, it returns as it is. If it's less, it returns 0. 78, we pass it to ReLU, it returns as 78. Okay, and the output of this axon will be 78. Okay, that's very simple, no magic. So you will pass some numbers here, multiply, add them, pass the activation function, and then you pass 78 here. Okay, and then the same happens here. 78 plus some other numbers that have been computed, like 0, 15, I don't know, 110. Again, same summarization, and you can extrapolate that the same happens here, and that's it. You will have, I don't know, 200 here and 500 here. Which class do you think you just predicted?
The lowest one?
Sorry.
Yeah, the second one, because its value larger, just larger than the previous one. See, that's it.
We can use different activation functions in our layers, yeah? For example, we can use ReLU for hidden and linear activation for output, yeah?
Yes, correct. I just oversimplified all the settings for you so that it is simpler for your perception. Of course, here will be one activation functions. Here will be something like softmax. If it's a gross entropy, you will have softmax, you will have them normalized, and you will not have like 300 here and 500 here. You will have like 0.4 here and 0.6 here. it will be kind of pseudo probability normalized to a sum of 1. So if you sum up values of all the neurons in output layer, you will have 1, but in one neurons this value will be parts of 1. In one neuron it will be smaller than the other one, and then the class that you predicted was the largest value that's in neurons of your layer. That's it, no magic. See, that's just the multiplications, additions, and then argmax. That's it.
I have a question. How do we choose an activation function?
Based on experience and luck and India developers' manuals.
So basically we guess.
When you're non-experienced, you guess. When you're experienced, you have some intuition. You can see here some example of activation functions. You can have a linear one that we just talked about. You can have a unit step in several forms. You have logistic that we just talked about, and hyperbolic tangent. Evolutionarily, some why people first used a hyperbolic tangent. It was precise, but it was very hard in terms of computation. It was a lot of computing time to compute it. You see here the derivative is not the simplest one. Yeah. Then people switched to sigmoid. It was simpler, right? The derivative is a bit simpler, but also non-trivial. The results were a little bit worse. People just added more layers and the results were satisfactory or better. And then people even simplified it. They created something that is ReLU. ReLU is a half of a unit step, left side, and half of a linear, right side. So you have a line to the left. So anything that is less than 0 is 0. Anything that is more than 0 equals to itself. It's ReLU. It's super simple, right? And then people just added more layers and it worked. And nobody knows why it works, okay? To this day. Now we will talk about forward and backward propagation. Forward propagation is exactly what we've just discussed with you. You take a sample, you pass x1, x2 into the network. This value is multiplied per weights. Weights are passed to activation functions so that you have activations here. See, activation is features multiplied per weights, then passed into the activation function. This is already sigmoid activation functions, right? And then you compute some value. A1 from X is called activation value. Activation of this neuron, yeah? Activation is what you get after you pass a sum of all the inputs into the neuron. You pass it to activation function of a neuron, and the value that you receive is your activation value. These activation values then become new inputs to a following layer. You see, it's a third layer, output layer. And for this output layer, x1, x2 are just activations from previous layers. Why here only 3 layers are shown? Because everything else works exactly the same. Okay, no magic, unfortunately, no magic. You multiply your A11 of X and A12 of X per weight of this plus A12 of X per weight of this weight plus bias term multiplied per weight of a connection of a bias term to the next layer. You sum it up, you pass it to activation function. In this case, activation function is sigmoid, see, 1 divided per 1 plus exponent of sum. Then, of course, you do not multiply path of each activation for every layer. That is too computationally expensive. It takes more time. What people do and how it works, they join all the input values into a vector, all the weights of all the layers into a matrix. See, that's just the weights of the first layer, weights of the second layer, and then they just do vector multiplication. They multiply vector per matrix, and they pass it to activation function. See, and you get the same result, but in several, much simpler, less actions. Vitaly, Alexander?
Yes, but where is the bias in this formula?
Plus one? Plus one?
Plus one. Yeah, plus one is bias. Yeah, plus one is bias.
Okay.
Okay? And this is how you get h from x. No. This is a1. You get this last a1. Then you get h of x, and then h of x is, remember I told you, 300 and 500, right? Then you select 500, and then you try to understand how far you're from through labels. You need loss function. This is a loss function. This is a, who will say which kind of loss function is it?
Once again.
What kind of loss function do you see?
MSE?
Here? Right, mean squared error. This term doesn't matter. You can divide by 2, you can divide by number of samples. It doesn't matter. Right, so you subtract from the true labels, y true labels, ground truth. So you know the prices of the flats, real one, that this flat costs like $800, that flat costs $300, but you predicted 500. And then you take the real price, 800, and you subtract the predicted price, this 500. And you get 300, and you square it. See? Then you got loss. Then you got to measure how far are you from the desired place, right? So you compute this matrix, and then you do something that is called backpropagation. Backpropagation starts only after you compute this value. I computed this value, now it's 300, right? Now I can do backpropagation. Backpropagation happens only after forward propagation, and during backpropagation, something that is called gradients are computed, and these gradients are used to update your weights. Remember, we started from the question, what weights do you take to start? And I told you, hey, random numbers between 0 and 1. We don't know what will be there, but we want to start from something. So you start from something, and then you upgrade them. And this is how we upgrade them. We compute gradients, and we subtract these gradients from these weights, the initial ones. Because this loss function tells us how far are we from the desired point in space and time, right? And this distance is exactly for each gradient, how should we change each way to be in this point where we want to be, to make the prediction precise, right? But it never happens because for every gradient, it's computed without taking into account the impact of other gradients. So we always miss, but with time we miss less and less. How are gradients computed? Gradients are computed according to the chain rule. Chain rule is a very loud name and very scary name if you pay a little bit more attention. And if somebody from you attended math classes in school, well, they should know what is it. Who will say what is it?
It is the rule to take derivative of the function that like takes as an input another function, which is just a rule.
Right, that's a rule how you differentiate the function of another function. You decompose them, you want to decompose them in two independent functions, and then you differentiate. First, you differentiate f from x. See, you differentiate f from x by x parameter, right? And then you differentiate g by f. So I don't know, you learned it in school. In the United States, this is super very complex topic. They all scared to talk about it. I think their schooling is not very good, to be honest. Right, you studied that. Who studied in the Math Lyceum? That's 9th grade task. Who studied in regular school? It's a 10 or 11th grade task. When you learn differentiation, you learn like if you have x plus 1, you differentiate it, you have what? Constant differentiated is 0, and x coefficient between x is 1, you will get 1, right? If you have 5x, you will have 5, right? If you have 1 divided by x, you have minus 1 multiplied per minus 1, right? And then you have something that is cosinus from 5x. Then you, wow, what should I do? What do? You differentiate separately. You differentiate first 5 from x, like this part. So let's say you have cosinus from 5x, right? And you want to take on a first order derivative, right? Who will tell me what will it be?
Minus 5 sinus 5x.
Minus 5 sinus 5x.
Yep.
Very good. I forgot, is it if we differentiate sinus, it's minus cosinus or vice versa, so we will believe you, but I want an intermediate step, right? How did you get it?
First time I've taken the derivative from the internal function that is 5x, and I multiplied that by the derivative of external function that is cosinus of 5x.
Correct. Cosinus will be minus sinus, and 5x derivative will be minus 5. Okay? And this is what is written here. Not more, not less. Why do you need it? You need it because h1 from x is a function of a0 plus a11 plus a12. Okay? And loss function is a function of h1x and h2x. Okay? Doesn't it sound familiar? You have a function from other function, and other function is also function of other function. J from W, right? Which in its turn is a function of H, and H is also a function from weights. See? H is function from A, yeah? And then H is a function from A. Okay, from A, what? A over a second layer, A2. And then all of that is a function of A1 from W. That's it. Function number 1, function number 2, number 3, number 4. That's it. Okay. And what's important is that we calculated that it is 300. Remember? In this fake example, I told that it will be 300 and 500, and then the true label is 800, and we subtracted. It was a square. My bad. So let's for example, the true label will be 800, and the predicted one. By the way, it's a regression. We have classification. Please forgive me. And squared by the number of 2, you will have 9,000. I lied to you, so 9,000. Right, because you have 300 squared. Oh, my bad. It will be 90,000. Right. Right. So here you know that it is 90,000. What do you do next? You resolve this equation. You take these derivatives for each layer and you resolve this equation. That's it. This is how you compute. But pay attention that these are matrices. This is a matrices. So you resolve matrix equation. Do you know how to resolve matrix equations? You must know. You must know. It was part of your school. Okay, so no magic. Having this value, you can calculate value first. Yeah, of course, you cannot calculate this. You have to calculate first this, then you calculate this, then you calculate this, then you calculate this. And each of these subparts will be your gradients. And your gradients will show how should you update the weights. These ones. Let's continue. Backpropagation. So we figure out how to do backpropagation. Now it is shown here in formulas. To summarize, you recursively take this complex function differential. Yeah, it's all together. Yeah? First, you initiate weights with the guess. You do forward propagation. You calculate all the layers. You calculate loss function. When you have loss function, you start to decompose it back, like differentiation. Yeah, you first look at the loss function as a function of a last activation layer. See, A2, and you can derivate it. You can say, hey, this is because this is your loss function, right? If you take first derivative of a loss function, it will be what? 2 multiplied per 1 second multiplied per y minus h, and inside these brackets you will have 1. Hence this value. Okay. And then you know how much is it? It is 90,000. So you can and you know what is y per each activation. So you can calculate gradients for each A. Okay. And then you do step back. Then you do the same. Then you know values of A's here, and you do step back, and then you know can calculate the values of this A. That's why it's called backpropagation, because you calculate from backwards to the initiation layer, to the input layer. Okay. Backpropagation. You calculate gradient per one example. It's a sum of gradients for all example, and this is an update or rule in matrix form for all the gradients. Okay. What is this? It's a learning rate. This is the gradients matrix. Why it's delta? Because those are gradients. Those are differences. Don't be scared of the word gradients. Gradient is just a difference. And these are the old values. So these are the values that you started with, some guess, and then you slowly start to improve your guess until you found something for which a loss is negligible, or it is less than the threshold that you set. It's less than 0.0001. If the loss, this loss, is smaller than something, algorithm stops and it tells you, hey, this is a good enough guess. Yeah, it will never tell you the exact number, but it will give you some good enough. Last thing that I had to talk about are dropouts. By the way, do you have questions regarding anything of this? This was the hardest topic in this course. Yes, Danilo?
I have a small one. In the last formula, we've seen the alpha, which is the learning rate, and the W, which is the previous values. But
matrix of weights. W is matrix of all weights.
And
M number of samples.
Okay, M number of samples. That's
alpha is a hyperparameter. You cannot see it anywhere. It's just something artificially introduced. The problem was that if you don't, learning rate is a value between 0 and 1. It is 0.1, 0.111 usually. It was introduced intentionally because if there is no like slowing down of the gradient, you overstep it so much. Remember I told you that when you differentiate one weight, it doesn't take into account impact of other weights. Like the method optimization thinks that every parameter is independent from each other when it tries to optimize one parameter. Then the other parameters like harm overall performance. So you need to make iterations first, and second, you need to make it slower. Otherwise, it overjumps the optimum. And this is another parameter that you have to guess, unfortunately. Well, you will not guess, of course. You will put some optimization algorithm and say, hey, try like this number, that number, and say me what is better. Okay. Then one more thing that I have to explain is dropout. It is important in the scope of dense, fully connected neural networks. Because it helps to avoid overfitting. See, dropout randomly for one epoch, it turns off some portion of neurons in each layer randomly. So these neurons were turned off randomly, but important point for whole epoch. So all the iterations within epoch happens without these connections. Some connections are deactivated. They are not multiplied, not propagated, neither forward nor backward, and the weights of these connections are not changing. It is done aiming to remove overfitting. Overfitting is network tends to stick to some successful scenarios, and some subnetworks are created inside the network that stick to some scenarios. And it is harmful for a generalization performance, so you need to somehow temporarily destroy this internal dependencies, so the network tries to find some other features. In general, when you apply dropout, the train accuracy drops, but the test grows, and it also helps you to prevent overfitting. This is just one of the ways to prevent overfitting. There are many ways to do it. This is just one of them. Overfitting, when you fit perfectly or better than you should the trained data set, but the accuracy on test data set suffers. It wishes to be better, right? And you need to somehow decrease performance on train, but increase on test. And dropout helps with this. Now I wanted to show you the implementation, initialization of artificial neural network model parameters. So this is something that you will code in your labs. you have, see, number of inputs, number of outputs, and number of hidden layers. Those are just numbers. You see, it's just values in Python. Then you create matrices of weights. Matrix of weights 1, first layer. This one. This one. It's just a set of parameters, right? And you make random initialization, random numbers, and see, you create matrix where you have number of inputs, number of hiddens, and then you create, it stores all the weights in this layer. And all the hidden layers. Number of inputs per number of hidden layers. Square matrix. Then you create biases. See, it's a tensor. Torch zeros. You initiate them with 0. Requires gradient. It means that these values will be updated with mathematical optimization later. You can freeze them if you put requires gradient false. It means they will be frozen forever. Not forever, but until you change it. See, and also you rand n gives a random number between 0 and 1. And then you multiply it on this multiplier to make them a small value, just a value between 0 and 1. Then you create in the same way a matrix of weights of another, of the second layer. This layer, remember, second layer, an example. Second layer, you still have one neurons connected to other neurons, and you have weights here. So you put them into the matrix. Here, second layer, second bias, and then just combine all the parameters in a matrix of parameters. How many weights in the first layer, how many weights in the bias, weights in second layer, bias of second layer. Then you define activation functions, ReLU, see? This asks, are they zeros? And then you max out. Yeah, you take maximum of, is it a 0 or a value? If it is any value above the 0, non-negative, the value of x will be taken. If it is less than 0, the 0 from A. If it's A value is smaller than 0, then x will be taken, okay? And then you define the model. This is neural network, by the way. So x are parameters, are income parameters. The one that's these ones. Square meters, how many windows, proximity to the center, the ones that we were discussed with you. You reshape them. Actually, it's a transposition or something. You need to do it to be able to multiply it using matrix multiplication per weights. You know that you cannot multiply matrices that are of equal size. I mean, if it's a 3 per 3, you cannot multiply by 4 per 4. They're incompatible. There is a matrix multiplication rule that the middle dimension must be equal. You can multiply 4 and 3, 4 per 3 matrix by 3 per 4. It will be 4 by 4 matrix. Here the same, you reshape it so that we can multiply it using matrix multiplication. See, plus bias, and we put it into ReLU function. See, multiplication of weights plus bias and put into the activation function, right? It was magic here. Now it's a very simple code here, right? Does it look familiar? Then it's just another layer. So see, you multiply it, and H is your matrix of activations. Then you multiply your activations per set of another weights, plus bias. That's it. And what will happen if you have 100 layers? Somebody.
The same
Okay.
thing, but 100 times.
You will have 100 rows of like this. That's it. And probably you will think about, hey, probably I have to write a for loop. That's it. This is artificial intelligence. So if somebody asks you what is artificial intelligence, you can with a high confidence respond that this is a multiplication of matrices. Okay. Then loss function. Cross entropy. You do training, many epochs, you remain do the same number of epochs, and learning rate. In this case, we just picked up as our best guess. Maybe they are not best, but in this case, we just selected something. See, then another important part of all of this is the optimization algorithm. In this case, it is stochastic gradient descent. This is something new. This is something that computes gradients and updates your weights every time, every epoch. So you pass params and it changes params using gradients and losses. And then you can see that with time, performance of your algorithm improves. You can see it by the decreasing loss function. It's loss on train, increasing train accuracy, and increasing test accuracy. If your train accuracy doesn't grow, but test accuracy grows, it's still fine. The main point is that test accuracy grows.